The 2-nanometer race is not really about nanometers, it is about whether Intel's architectural gamble can beat TSMC's execution machine. Intel is trying to turn one foundry node into a corporate redemption arc. TSMC is trying to make the same transition look boring, controlled, and inevitable. One side is selling architectural aggression, the other is selling trust at industrial scale. The scoreboard is already crowded. Intel says 8A entered production in 2025 and 8AP entered risk production in 2026. TSMC says N2 started volume production in the fourth quarter of 2025. Both can claim momentum. The question is, whose momentum turns into paid wafers? First, ignore the label. 2-nanometer does not mean every feature on the chip is 2 nanometers wide. Modern node names are shorthand for a bundle of trade-offs: density, power, performance, cost, yield, and design rules. The race is not a ruler measurement. It is a manufacturing system. Both companies are moving past the FinFET era. TSMC's N2 is its first node with nanosheet transistors. Intel's 18A uses RibbonFET, its gate, all-around answer, paired with backside power delivery. The transistor is becoming three-dimensional, and the power grid is moving to the back of the wafer. Now, Intel's gamble. Intel's pitch is simple and risky: change multiple hard things at once. RibbonFET improves transistor control. PowerVia moves power delivery to the backside, reducing congestion above the logic. Together, Intel wants a cleaner signal path, stronger voltage behavior, and a node that makes customers believe the comeback is real. The numbers are exactly why the story is exciting. Intel says 18A delivers up to 18% higher performance at the same power, 38% lower power at the same performance, and 30% chip density improvement versus Intel 3. PowerVia is advertised as reducing worst-case voltage droop by as much as 10 times. But foundry customers do not buy slides. They buy predictable design rules, mature libraries, reliable masks, packaging options, and confidence that the wafer starts will not become an expensive science project. Intel's challenge is not invention. It is trust transfer. TSMC's counterpunch is quieter. TSMC says N2 started volume production in fourth quarter 2025 as planned with first-generation nanosheet transistors. Semiconductor Engineering reported that TSMC claimed more than 20 customer tapeouts already received, more than 70 in the pipeline, and defect density reduction ramping better than N3. The trade-off is sequencing. TSMC moves to nanosheets with N2, but its superpower rail backside power delivery comes later with A16. That looks less dramatic than Intel's 1-2 punch, but it also reduces integration risk. TSMC is not trying to win the loudest architecture contest. It is trying to protect the ramp. Then comes the bottleneck. Under both roadmaps sits ASML. Its High-NA EXE systems use a 0.55 numerical aperture and target 8-nanometer resolution. ASML says the platform supports high-volume manufacturing in 2025 and 2026, starting at the 2-nanometer logic node. But a tool is not a yield curve. It has to be absorbed by an entire factory. This is why the 2mm race can look confusing. One company can lead in transistor ambition. Another can lead in production confidence. A prototype can beat a competitor on paper and still lose the business if customers fear schedule slips, low yield, or missing ecosystem pieces. So who wins? Intel wins the narrative if 18A and 18AP ramp cleanly, prove PowerVia at scale, and pull real external foundry customers. TSMC wins the market if N2 becomes another boringly reliable volume node. The most likely near-term outcome is split. Intel owns the comeback story while TSMC keeps the default trust premium. The brutal lesson is this: advanced chips are not won by being first to describe the future. They are won by making the future repeatable, wafer after wafer. Intel has the more dramatic bet. TSMC has the deeper habit of execution. The CNM crown goes to whoever turns physics into dependable supply.